Hello everyone and welcome to this Midas Civil webinar. My name is Adam Kane. I'm going to be taking you through proceedings today. First of all, I want to do a quick sound check, so if you can hear me and you can see the screen, please raise your hand or place a comment in the GoToMeeting dialog box. Shouldn't have any problems. We've already carried out a few tests and everything, so once we've done that I'll just continue. Right, thank you. Today we're going to be going through the design of bridges to Eurocodes. We're going to be focused on 4 different bridge deck types and 4 different types of design. So I'm just going to continue. If you've got any issues or you would like to ask any questions or you need technical support or anything, you've got the details just on the screen there and the phone number and the email address. So just a few ground rules, general housekeeping, GoToMeeting. I'm sure you've all done this before. If your computer's set to mute, then you probably won't be able to hear me, but if you could just either raise the volume or just raise the volume in the bottom right hand corner. If you want to maximize the screen, just hit on the 2 overlapping boxes. If your screensaver happens to kick in, then it is probably set on, so you might want to set it off or just keep on wiggling the mouse. Just using the GoToMeeting dialog box, just click on the red arrow to minimize it. It'll go down to a thin strip. If you want to ask any questions, just type them in the chat box just there, and we will respond to any questions either in the webinar or afterwards. So here's the contents today. We're going to be going through steel member designs. We're going to be focused on a steel bridge. Then we're going to be focused on a composite steel member design to Eurocode 4, where we focus on the Philippine deck. And then we look at the reinforced concrete member design in the forms of piles and abutments and things like that to Eurocode 2. And then we'll also look at the pre-stressed concrete section design to Eurocode 2 for a box girder bridge. So just a slide on the steel member design to Eurocode 3 and the classifications of the cross section. So you have your ultimate limit state and you also have your serviceability limit state, and this is the step-by-step process throughout. So in the ultimate limit state, we jump on the tension forces, the compression, the bending moment, the shear, bending and shear, bending and the actual force, the bending, shear and the actual force, and the buckling resistance of the member. So this is under the ultimate limit state. During its serviceability stage, in the limit states here are the vertical deflections over time and the horizontal deflections as well. So just focusing now on the classification of the steel sections. So I'm going to go through class 1 through to class 4, and the main focus of these is on the potential for buckling and everything like that. So class 1, which has a high rotational capacity and it will go into its plastic state before buckling. And then you've got the class 2, which has a limited rotational capacity, which will go into its plastic state before buckling, but then will go back down into its through its elastic state when it's gone past the failure stage. Class 3, which local buckling is prevented the attainment before it reaches its full plastic state, and class 4 will buckle before it's even reached its elastic state. So those are the classifications of the section. This is all from the Eurocode 4. You will find the table just below, so table 4.2, which is the class of sections according to the class of compression rates. As you can see, you have a vertical and horizontal axis of the class of the flange and the class of the web. So what will happen here is based on the selection. So say the class of the flange, the class is 3, then you go across. But if the web is in a worse state, so say that the web is a class 4, then the section will be considered a class 4. So whatever is the worst case, so say the flange has got a 4 and then the web has got a 3, then it will always be the higher classification that is selected. So this is what we're going to be focused on first. So what we're going to do, this is just a simple steel truss arch bridge, and we're going to be focused on today. As you see, it's got the main girders, the cross girders, and also the bracing, or what can be called the struts. You've also got the bracings on the top there as well. So just to take you over into the modelling space. So just to show you some of the sections and the main girders. So with Midas Civil, if you just double click on it, it will highlight it. As you obviously know, if you're an existing user, these are cross beams, and we can go through the assignment, all of them, and the properties. So you can see that's an I section, and it's a user defined. So we can also do the user defined sections. So I just want to look at the materials and show you that everything is defined as steel. So this will be a key point later when we're doing the design, because the program automatically simulates that it is all steel and just selects all the steel sections for the design. So just looking at the results, I just want to look at the different load combinations. So these can automatically be generated, but I have created a couple of load combinations here at the top. So just this for the strength, stress, and the serviceability. These are from the code. So just to go through all the automatic generation, and you can automatically do that as per the Eurocode or as per the BS standard. I'm not going to do it in this case, I just want to continue with the two load cases that we have. So now just looking at the design and going for the steel design. So it's going down then steel code, so we just want to select that as the Eurocode 3. So now we know that's already been predefined and selected. Then we could just go down for the partial safety factors. Now these can defined, and you can change them as per the code as well. So as you can see, we've got the classifications there for class 1, 2 or 3, and also a class 4. So we can just change those. Now just looking at the modified steel material. So if the Eurocode states if the flange is less than 40 millimeters, so the web is less than 40 millimeters, then the strength of the steel is 355, and if the flange is more than, or the web for that matter, is more than 40 millimeters, then it's 335. So this is the yield strength for greater than 40 millimeters and lower than 40 millimeters. So we can define the steel, as in the steel member, to be a column or a beam manually. As you can see on this arch, then as it's going up through over the arch, then you need to define them. So I just want to go into the sections and just select the arch and make sure that the program or Civil understands that it is a column and not a beam. So that's been defined there, and that was under the common parameters. Right, this is the bracing or the struts, so we can define them as bracing, so when it carries out the design it will understand that they're bracing. So there you can see it's actually come up on the screen. So for the buckling and the slenderness, I can input the effective length, so we can change, and as you see you've got the LV and LZ for the direction of the lateral, well, for the buckling, and you've got LB for the lateral buckling length as well. So in this window it literally shows it that you can do it manually, but in this case we'll just let the program automatically define it for us. So we can also define the spacing between the transverse stiffeners of the section. So obviously you see the main girders there, so you can actually define the pitch or the spacing between each one. So as you can see there, you've got it labelled as 2 meters, so we can just define it and bring them closer together. So just look at the serviceability parameters and go down through. So we can check the deflection control for beams, so we can set it at different values. So we've got it at L over 250. Depending on the code you can obviously change it, so we can look at the deflection control for columns as well. So just go down through the steel design and do a steel code check. You see it's just selected all the members. It's carried out a check, so as you can see it's all highlighted in blue, so that means it was all passing. Now we can look at the graphic, which is just a quick summary report, just to look at the members forces, design parameters, and checking the results, going down through, so we can look at all the bending resistance, the combined resistance, and the shear resistance. Then we can even do the deflection checking for the results as well. If any of these are failing, it will be highlighted as red. So we can also look at the more detailed report as well. So just going down through this, as we had on the slide, and we had the work through for the ultimate limit state and the serviceability limit state, you can see that we've got all the headings and the titles. So I just want to highlight these. So you can look at the section properties, look at the design parameters, the strength evaluation, the material properties as well, working our way through. So these are obviously key with your upper limits and lower limits. We can have the forces and moments, and you can also see them for the buckling and the direction for the lateral buckling as well. You've got the sign conversion for the strength, the classification of the hot flange of the section. So this is where we have our classification. So as you can see, it's marked as class 1, and it is as per the Eurocode 3. So it even gives you the code and where it is in the table. So from the bottom flange, you can see that it's actually not determined, it's not classified. This is because it's in tension, and buckling will only occur in a steel section when it's in compression. So just take you further down the list, so we can check the actual resistance for the code, and we can also check the shear resistance as well, and all the calculations as explained. They do have the actual code and where it can be found within the code as well, making it easier to cross-reference. So just focus on the shear buckling check, which is where the web shear buckling occurs. So you can see that we've this is where the transverse stiffness come into play, because to reinforce the web when it's actually under shear. So we've got the checking the bending moment resistance about the major axis as well, and then you've got the checking the bending moment resistance to about the minor axis. So obviously you've got your major and your minor. So here we have the combined interaction between the shear, the axial, and the moment forces. So they're all combined together. So the bending and shear, and the minor reduced design resistance of the bending and shear as well. So you've got the max and we can also check the deflections as well, going down through. So just look at the results ratio. So what we can do is check the capacity of the steel and the percentage of the utilization of the section. So I just want to select one of the steel girders and just select the elements. So as you see in the background, it's selected the elements and it's come out with the results. And here you have the capacity and the results ratio for the combined. And you see it's only got 33% capacity of the member is being used at a maximum. And then obviously you got your minimum down there as 0.24, which is 24%. So what we're going to do now is actually carry out an optimization of the steel section so that the capacity of the member is more effectively used. So here we have the member that we have selected, and what we're going to do, hang on, no, so just open up the box again, because we've got all of the steel members and we only have one before. So we can actually just select the ones that we want to optimize and make sure that you can see all the capacities there of each individual member. So these are the flange and web thicknesses that the software will select when carrying out the optimization. So we can highlight them and we can kick them out of the list depending on what we want to do and how we want the affect the width of the flange. So just to carry out the optimization, you just have to reanalyze the model a second. Just bear with it. We'll have a Word document, or we can create a PDF out of this, or we can create a text report. So just to save that. And there you can see that the sections have been optimized and the weight of the sections has gone down and the capacity of the members would have gone up. just to explain that it iterates it down as per weights for the optimization as well, just to let you know that. So just go through the optimal design for the weight sum. As you can see, that was the original, and then you've got the first iteration, or the first design we did for the optimization, and the weight's been reduced. Then we can look at the ratios, and as you can see, the ratios have dramatically increased. So the red indicates the original, and the green indicates the actual optimization that was carried out. So now just going back into the presentation. So this is the next bridge that we're going to focus on, and this will be mainly these are the main girders, and these are the more common practice in the UK. So you've got your main girders, you've got your cross girders as well, and this is where the stiffener plates will come affected for the buckling effect. So when a vehicle goes over it, then if it is its centre span, which I'll indicate with the mouse, so say there was a vehicle there, then buckling can be created in the main girders to the side where they will tilt in. That's why stiffener plates are used to hold back the forces and the moments that are actually attributed to the sections. So just going to bring the model over. So as you see, if I go to the side view, then you can see that it's a tapered section. So each section is modelled within civil. You can see it tapers from one end to the other. We can look at the actual each individual section, which is individually placed into the program, which is customized, your user defined. So just to show you, what we've done is just skipped everything and just going to go straight to the still code check, which is the best way of doing it, because everything's exactly the same as it was previously. So just want to show the section that will be focused on the lateral torsional buckling in this one. So just to go through the detailed report, and we just flick through that, and I just want to go to the lateral torsional buckling, which is the key for a bridge like this, and is why you input the stiffener plates for the design. So just finding it now. So just want to check the torsional buckling resistance. So this is taken from the Eurocode 3 -05 and clause 6.1 and 6.3.2. As you see that you've got the critical moment for lateral torsional buckling here, and as per the code. And that's the calculation. Let's get rid of that. So that was just the steel design for that one. Now we're going to focus on a composite steel design. So in this one, then it's to Eurocode 4 first and foremost. The ultimate limit states and the serviceability limit states are slightly different from the standard steel design. So for the ultimate limit state, we'll be focused on the bending resistance, resistance to the vertical shear, resistance to the lateral torsional buckling, the resistance to the transverse force because of the reinforcement on the web, and then you've got the resistance to the longitudinal shear and the resistance to the fatigue. For the serviceability limit state, then you've got the stress limitation for concrete, the stress limitation for the reinforcing steel, and the same for the structural steel and the longitudinal shear. So this is the two-span composite girder bridge that we focus on today. As you can see, we've got the reinforced concrete piles, you've got your abutments, and you've also got your columns there, or your piers, going up to a hammerhead pier. So it's going to bring over the GUI, the modelling space, and just go through the definition of everything and why it's all in place. So just show you how to define the composite section. So this is the composite section. So you can see that the concrete is on top of the I section, the girder. So you can just define that. You can also define the different throughout the different construction stages as well. So looking at the steel only on the deck, and then the concrete pours going across. Obviously you can split this up into as many different construction stages you want. You're not limited. You can see the effects on the structure. You can find the concrete and the steel to be in different stages as well, or different construction stages. So just the two different materials have been split apart. So you've got the steel going in first, and then you've got the concrete going in on top. That's where you define that for the combined steel and concrete section. So here you have the concrete deck. You can just isolate that for the composite, sorry. And we can look at the properties of the composite section. So you can see the 355 steels being used and C40 concrete being used. You can also do user defined as well in those special cases. So looking at the results and the load combinations, which are automatically defined for the steel, as you can see there, where they strengthen the serviceability of the sections as per the Eurocode. But we can automatically generate these as well, which we've done in this case, which we didn't do previously. So there you go, just close that. Just going over to design, and we can just go to the composite design. I'm just going to go through each of these. So the parameters. So these are the partial factors for each of the different materials that are going to be used for the construction. So you see the concrete, reinforcing, steel, structural steel, more structural steel, shear resistance of headed stud, which is the studs going up into the concrete above. We can also have we've got the design life set at 120, and a fatigue check will be carried out for the 120-year design life. So it's moving down through now the design material. So obviously we've got the composite section here, and the steel, and you've also got the yield of the steel, so the upper limit and the lower limit. That's when we go back to the 40 millimeters. So above 40 millimeters and below 40 millimeters. So we've got the concrete material selection. You've also got the compressive strength, which is defined as well, and the reinforcement in the concrete, which is you can classify the rebars, so the different classes for the Eurocode. So going down to the longitudinal reinforcement, I'm going to do these one by one. So you can see here that we've got the typical main girder, which is so that's we just go to the guideline in, and that is the spacing, and we've also got the length going across, and we could just do the number of bars that we're going to put in place as well, and select which bars we want. So just add those, and it should come up on the screen. I see those have been added there. So just to close that, right. So now looking at the design position. So this is where you select the members for design. So as we've just selected everything and we've already done that, then we can skip past it, but it's just showing you the feature. So you just look at the position for the design output. So this is where we look for the most critical member, and then you can get a full design report, which is detailed and will be line by line. So within this section we can just select the most critical point, and you will get a full Excel design report. So just looking at shear connectors going throughout, so this is where we can define the different shear connectors and the total number. So we can just set a number, and you can set the tensile strength of it, and also the diameter of each individual shear connector. So just 20 millimeters, and then we can select the height of it, the overall height, so 10, and we can just set the center to center, the distance between them, and also the spacing. So here we have the transverse weft stiffeners, just to show you this is where they're defined and give you each value. So obviously DS, and then ST, which is the distance between the two of them, center to center. So it's going straight down through again, and we can look through the transverse stiffeners as well. So we set the height and T is the width of the section. So that'd be the width of the actual. So as you see there's the web, and you can see the stiffener coming out. So that is the HT, which is the height, and then you've obviously got the thickness, which is marked out as T. So we can also do the spacing, which is the pitch. So I will define that as well. So that is just the spacing between each individual one. So we can look at the transverse stiffeners at the end supports, or of the end supports. So just select the supports at either end. So you can see the rigid end post, and that is selected, as you can see, at either end of the structure. Define them, so you can select the length or the height, and then you can select the thickness of the transverse stiffness, and also the eccentricity of the end post from the supports. So now just to look at the types of load application for the plate girder. So just to take you back into the presentation, just show you that in the diagram. So these are the different types of loading conditions near the supports. So you've got, these are all per the Eurocode 4, and you can find them in figure 6.1, which is defined underneath. But that is the concentrated load in the type A, and then type B would be the concentrated load over a bearing, say. Type C is a load where no stiffeners are present. So going back into the program, I'm just going to get out through the list again a bit further. So we're just going to focus on the lateral torsional buckling data. So you see these are the distance between the springs, and you can, so this is as per Annex D of Eurocode 3 Part 5. So you can enter the spring stiffness as per this annex in these values here. So just by taking the code and then inputting the values. Then we can look at the serviceability load combination data, which is automatically defined within the program, but if you do want to do them yourself, so there you've got the quasi-permanent, you've got the frequent, and you've also got the characteristic. You find that in the code as well, and then you've got the design tables with the bending resistance. You can input, so you can just look at the -J fend, and it will give you the classification for each of the top and bottom flanges, and also the web and the section class overall as an average. So as you can see in the top entry, that the top class and the bottom class are considered as 1, the web class is considered 3, so in effect it's taking this section class as 2. Another way of saying this would be that it's only marginally taken over into 3, so that means it is averaged it out and taking it down to 2 as well. So this is just for the composite, which is not the same as the classification for the steel bridge that we did earlier. So these are the moments before the composite section, after the composite section, and you have the plastic moment and also the elastic moment, so EL for elastic. Take back into the model view. Also look at the resistance to the vertical shear. So it's got all the sections there. So here you have the classes once again for the vertical shear. So here you have the actual force, the moment, and also the shear force as well. So the software takes into account the combined actual moment and shear combination. You've also got the plastic shear resistance as well, and the shear buckling resistance. So let's go down to the next table. So we've got the stress limitations. So this is the table for the top and bottom flange of the structural steel. You can see there that you've got the normal stress, and this is for all the girders. So you've got and that's the allowable stress as well. So as you'll see that you've got the normal stress is less than the allowable stress, and if it wasn't, then it would be highlighted in red. So it's failed. This would be the shear stress, and that's the allowable shear stress as well. So you just compare those against one against the other, and that is the normal shear stress combination and the allowable as well. So then you've also got your concrete deck, which is much the same way, and you've got the reinforcement in the deck as well. So just then you can print the results, and here I've just got one already open. So here you see that we've got the results in an Excel format, and you've got the section information, and you've also got the before and after, and you've also got the cracking as well. So just the bending resistance, going all the way down through, and you've also got the plastic, the plastic moment there. You've also got the resistance to vertical shear, and you've got the vertical shear as well. So looking at the web shear buckling as well, then we can also see the plastic shear resistance of the member. Then you've got the resistance to lateral torsional buckling as well, and the resistance to the longitudinal shear. So key point is this is for the shear connectors, and where the longitudinal shear occurs between the concrete and the steel deck. So the shear resistance for a single connector, as you can see there, so that is just multiplied for the additional connectors compared against the input or the results from the software. Then you've got the resistance to the fatigue, you see the moment, and going down through, and then we've also got the stress limitation, so that's in the structural steel. Then you've got the stress limitation in the concrete of the slab, and you've also got the stress limitation in the reinforced concrete as well. So just the final one is the longitudinal shear for the serviceability limit state. So now we just looked at all the results, we're going to look at a special case composite section and a Philippine deck. So this is the Philippine deck here. So, and we'll look at the steel I-beams, which should be a class 1 or a class 2. So that's anything that resisted buckling going into the plastic state. So just to bring across the modelling space, it's already opened. So here's the actual model, here's the Philippine deck. As you can see that the steel members are completely encased in the concrete from the front there. So just to look at that now, now these sections have been defined in AutoCAD and then brought across into the section property calculator, which is we'd showed in a previous web-based session and has been uploaded to YouTube, which is called, well, which has got Philippine in the title. So if you want it, then you can look at it. Just to go through the different construction stages, so just for the steel only, and then going down through to the deck casted around it, and then the parapet surfacing and everything like that. So just going to the post construction stage. So composite design. Now we just want to look at the longitudinal reinforcement. So this is the longitudinal reinforcement that's been put in place. So now just look at define the flange and the web. The program doesn't define the flange and the web automatically, so they just need to be defined within this dialog box. So as you see, you have the top 1 and 2, which would be defined as the outstand, and then you have the web, which is defined as the internal. So just had to clarify that to bring it up. So then you can just go down to design. So it's just going to take a couple of moments just to go through this, if that's okay. Just to wait a couple of minutes, it might take a minute or two, I'm afraid. Just bear with us. So that's complete. We can just continue. Let's go down and look at the bending resistance. So Look at the parts, and then you can see the classification is exactly the same. So each class is defined, and as we stated, it should be class 1 or 2. So you can see the moments and everything like that. So just to take you back into the PowerPoint presentation. So just looking at the reinforced concrete design to Eurocode 2. So we're looking at the ultimate limit state with the moment resistance and the shear resistance, and then the serviceability limit states for the stress of the cross section, the crack width, and also the deflections. So the transverse rebar distribution in the grillage model, which is for the Philippine deck, and then we look at the concrete piers, which we had in the two-span structure, concrete diaphragms, and also the design of concrete piles. So first of all, we're just going to focus on the column design and the pile design in this model. So just going up to reinforced concrete design, we're just going to jump straight into it. This has all been modelled and defined, so just go down through the partial safety factors and the concrete. So as you see, we've got the reinforced concrete there, the concrete there, and the material type. You can also look at the transverse reinforcement and everything. So column section data for checking, just to click on that, and then we've got the definition of the column and the size of the rebar that we require or we would like. And we've also got the piers as well, so what we defined in the piers. So we just predefine that. So just to show the boundary conditions for the point springs or the pile spring supports. So as you see there, that's for show the soil structure interaction. You can also see the surface spring supports for the strip footing as well, that we can also carry out a design for. So just to undisplay those. So now we've got the piers selected. Just want to do the check. Also want to select some of the pile as well. So just go down to concrete code check and then column checking. So we've already got the rebar in place, and it's telling us that they're passing. So obviously if it's highlighted in red, then it'd be failing. So just to pick up the quick graphic there we've previously shown, and you can also see the applied force, the actual forces, the PM interaction diagram, and the shear force resistance check. This also comes in more detailed as well, but we've shown you that previously. So just go down and you see the pier, and we can also look at the PM interactive curve acting in the MY and the MX. So there's the detailed report for just the pier. Going down through just to give you a bit of a focus. So you've got the section type, which is a solid round section. Then you've got the slenderness ratio, and the analysis of resistance for the biaxial load for the column, and you've also got the check-in for the moment resistance as well. The calculation for the shear resistance, so that's using the link data what we entered at the start. And you've got the calculation of the serviceability checks for the column as well. Let's get rid of those results. So we can actually see the section. You can look at the transverse beams. We just want to activate them. So these are the transverse beams for the deck. Going across, this is where the reinforcement is defined, so we can do the beam section data, and as you can see, that is the reinforcement within the member. So just to go back from that, so we can just carry out the beam check. And we see all the capacities and everything like that, just the same as we did previously. So it's just selected all of the plates. I should have just selected a few of them, but we're just going to check all of them anyway. So if you just bear with it a couple of seconds. Okay, so that's the checking being carried out. So you can see the graphic, we can get all the results, the moment capacity, going down through for the shear capacity as well. So just going back into the presentation. Now we're going to look at or focus on the pre-stress concrete design to Eurocode 2. So looking at the ultimate limit state for the moment resistance, shear resistance and the torsional resistance. Then looking at the serviceability limit state, so checking for the stress for the cross section at different construction stages, the stress for the cross section at the service loads, tensile stress for pre-stressing tendons, the principal stress at construction stages and the principal stress at the service loads, and then check for the crack width. So just to show you the model, we're going to be focused on the balance cantilever method, which is segmental construction and tapered, as you can see there. So just to bring across the model from the modelling space, and to briefly touch on the construction stages and also display the nodal loads and also the tendons as well, so we can flick through those through the construction stages and go throughout. So you see them getting added one by one, each individual section, each tendon. So just frozen the screen there, so we can go back to the base and flick everything back off again. And display the loads and also the tendons. There you go. So let's go to the section manager and the reinforcement within the section. So for each individual section as it's tapered, we can define the reinforcement. This will actually be done automatically. So this is the longitudinal reinforcement and also the shear reinforcement, which will be defined. So you've got your pitch there, which is the distance between the shear links. Then you've got the torsional reinforcement as well. It can be defined within that working window. And we can look at the just look at the design parameters. So that's the Eurocode 2, and we've also got the national annex or the British national annex as well. So just highlighting the serviceability limit state and the ultimate limit state as well. So you can just change those and that will come up through in the analysis and design is carried out. So just looking at the pre-stressed concrete design manual and the concrete grades that are being used and obviously the yield strength and everything like that. So just the serviceability load combinations, which are automatically defined if we've got the serviceability parameters put in place. So we just got the exposure class, exposure to the class crack width. So as you see there, we can look at the exposure class for the top and the bottom. Then we can look at the design tables and the crack or check the results. So that is the applied moment. So this is the bending resistance table. So this is the applied moment, the moment capacity and the ratio. And that is the area of pre-stressing steel. So let's go through and check the shear strength. So that's the applied shear strength, the shear capacity, the shear resisted by concrete, and the shear resisted by the steel stirrups. So we can export that to an Excel file as well. I just want to open that up. So this is the pre-stressed concrete Excel report that comes out. So this is the design conditions, design situation, section information, the material information, and then you've got the tendon profile information as well. and this is just for one section. So this is the positive moments. So look at the calculate the neutral axis. The software follows the strain compatibility approach for design. Then you've got the negative moments, the maximum shear or the shear resistance, and the minimum shear force as well. Go all the way down through for each section. So then you've got the torsional resistance. So the key, just going down through the key things, and the maximum torsional moment as well, and the crack width in the top and the bottom of the section. So we're going to look at the design results diagram for the solid fill. Just clicked on it there, so you can look at the components and the flexure, the shear and everything like that. So just going to look at the solid, click apply. So this is the applied bending moment throughout, and that's the capacity of the section. So you can see the applied bending moment against the capacity. And you can also look at the shear as well, and the min, and also the max. So there is a shear that's occurring, and there's the maximum shear capacity. So where there's gaps, there's just no shear connectors or shear stirrups been put in place. I'll just take you back to the presentation and just close. So I know we've gone way over. We'll answer. We've got a few questions come in. I do apologise. I can see them on the screen, but we're going to come back to them, or come back to you at a later time. So just send you an email or something. Thank you for attending this webinar on Eurocode design in bridges. Hopefully it's been very informative, and if you have any questions, then just either email us on the address on the screen, or just give us a telephone call. My name's been Adam Kane, and thank you very much. If you do want to get involved in some of the competitions we're running or anything like that, then please also email in. That is for the students and graduates. We're just trying to get more people involved with the inspiring the next generation. So hopefully, if you do have any questions about that, just please send in an email. But thank you very much for attending once again, and I look forward to the next one that we conduct. Thank you.